Boink.
My life is without direction.
What's that?
I said my life is now without direction.
Aimless and without direction.
I am no longer a vector. I only have magnitude.
That's like physics humor, it's like astronomical humor, it's everything.
Physics is the
Oh.
fact of my life.
Speaking of a funny joke that I wanted to tell you about that I made. So,
Oh my gosh.
yeah. So, over the weekend or something like that, I went to like Kroger and got some like alcoholic root beer. And so, I was making a joke and I was like, what are they called? I'm like, it's a root beer beer. It's a root beer squared. It's a beer.
Because it cancels out.
It's a root beer beer. Root beer squared.
There you
It's
go,
a beer.
that's, damn, that's.
Wait, I don't get it. So, okay, so it's a root beer. It's a, yeah, exactly.
Oh, it's like a square root.
Yeah.
Oh, okay.
It's a root beer beer, so it's a root beer squared, so it's just a beer.
Okay. This needs to go viral. Viral.
I wrote it on my board in my house just so people would like look at it and then get the joke, and I was like,
I think I told you guys my joke about what you get when you cross an elephant with a rhinoceros.
Elephant.
Yeah, albino.
uh.
Two viral jokes right here.
And you thought physics was a point.
That's right.
Physicists make the worst joke.
Which thereby means they are the best jokes.
That's true. Yeah.
There. Right there. No context needed here for us. So.
You'll need another video exam.
Yes.
We're on the spectrum where you're
That's good.
Thank you. Thank you.
So, where am I? Right. So, the mean free path for photons having wavelength lambda will be the average distance that they go along the beam before getting scattered or absorbed. You have something against averages.
I just heard during time I say the little brackets.
It's a friggin' average, come on.
It's more of like post-traumatic stress.
I guess so. Yeah. So that will be the integral from 0 to infinity of distance s times the probability of making it a distance s, which is p of s ds. So integrate from 0 to infinity of every possible value that you could go, s, times the probability of going that distance, p of s ds. That's what we'll mean by the mean free path. So we have expressions that we can plug in. We have an expression we can plug in for what p of s ds is. So we are doing a very specific integral. 0 to infinity of s capital lambda rho e to the minus capital lambda rho s ds. That's the integral we must do. Well, that is the integral from 0 to infinity of s times minus the derivative of e to the minus capital lambda rho s ds. Because if I take minus dds of e to the minus capital lambda rho s, that's going to give me capital lambda rho e to the minus capital lambda rho s ds. In other words, we can do this as an integration by parts. One way to look at integration by parts, courtesy of the author of the E&M text, who also writes the quantum text that we, those of us who are not named Dr. Andrew in the department use when we teach quantum. She uses a different book. But in any case,
There's a different text that we
There
could
is,
use.
there is,
Does that one have an example?
We use Griffiths for quantum mechanics.
Does that one have an example problem in either chapter 6 or 7?
I'm sure it does.
Because
Yes.
the McIntyre isn't.
You don't need examples when everything's clear. So anyway, so the rule for doing integration by parts, which I had never heard of before Griffiths did it, it's entirely equivalent to the usual u equals dv equals blah, 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 is that there's a boundary. Basically, you switch the derivative to the other piece and change the sign, and then there's a boundary term. So in other words, this is going to be the integral from 0 to infinity of e to the minus kappa lambda rho s dx. In other words, if I switch this, if I change the sign and switch the derivative to the other side, that would be ds ds, which is 1 e to the minus kappa lambda rho s ds. I can make that explicit. So equals integral from 0 to infinity of ds ds e to the minus kappa lambda rho s ds. So you switch the sign of the derivative and move it to the other term. So ds ds e to the minus kappa lambda rho s ds. And then there's a boundary term. In other words, the uv piece. So this would be the udv business here. So there's the uv piece, which is going to be minus s e to the minus kappa lambda rho s, evaluated between 0 and infinity. That's the uv piece. So u is s, and dv is minus eds, e to the minus kappa lambda rho s ds. So v is just minus e to the minus kappa lambda rho s. And then we evaluate between 0 and infinity. So of course that's 1. So that's a nice way to look at integration by parts. Instead, when u equals dv equals, the rule is move the derivative to the other side, move the derivative to the other term with it, and change the sign of it. And then it's just going to be this term times get rid of the derivative on that term because you're integrating the derivative. So uv, that business right there. I find that's quicker than when u equals dv equals and all that kind of stuff. Anyway, so when I do this piece right here, so this piece right here, what happens when I plug in infinity? I get s e to the minus kappa lambda rho. So so in other words, s blows up, right? But e to the minus kappa lambda rho s blows down, so to speak. Which one wins? Yeah, the e term wins. So that limit goes to 0. And then when I put in 0, that goes to 0 because there's a 0 right there. The s is 0. So in other words, this piece goes away. The boundary term goes away. And we're just left with the antiderivative of the other one.
You can do this.
I can do this. I can definitely do this. So this is just going to be e to the minus kappa lambda rho s over kappa lambda rho, evaluated between infinity and 0. So in other words, when I integrate e to the minus kappa lambda rho s, that's minus 1 over kappa lambda rho, e to the minus kappa lambda rho s. Or I can get rid of the minus sign and flip the limits. So I went from infinity to 0 instead of 0 to infinity. Well, when I plug in 0 on the top, what do I get? When I plug in 0, the top limit, I get e to the minus kappa lambda rho 0 over kappa lambda rho. What's e to the minus kappa lambda rho times 0? What's e to the minus 0, in other words?
1.
1. Yeah, so the first one gives 1 over kappa lambda rho. Isn't that what we wanted? The whole point of this, which you've forgotten by now, is we were trying to show that 1 over kappa lambda row, the E folding distance was in fact the mean free path, right? Because the other limit's going to be 0. When I plug in infinity, I'm going to get e to the minus infinity, which will give me 0. So, boom!
It's good, very cool.
Ba-bam! 1 over kappa lambda rho is in fact the mean free path, which, okay, fine, I said this equals this, yeah, but no, it's a reminder basically down here. So in other words, boom, check mark, we got what we wanted. The mean free path is the E folding distance. The photon mean free path is in fact the E folding distance. An interesting result to note.
My joke is gone.
Is that?
So my joke is gone.
Oh, your joke is gone. No, it lives on.
Oh.
Your joke is timeless. It's
Thank you.
immortal.
It's time break.
Yes.
Posted in textbooks everywhere.
So,
Don't be easy mathematical transition.
yes. So indeed, the mean free path is 1 over kappa lambda rho, and we can also say it's 1 over n sigma lambda using our other expression we had before. I'm not going to bother with the root 2 one here. And I think, I don't remember, it may not happen for photons because they're all going the same speed. They're all going the speed of light. So I don't remember. I think that may not happen with the photons though, for that reason. So, Foxworthy, and here, the sigma lambda here is what we call the photon absorption cross-section. It's how big the atom looks to the photons, essentially. What effective surface area does it present to the photons? Now, of course, in SI units, cross-section is measured in square meters, but those are very inconvenient units on an atomic scale because certainly the effective cross-section area of an atom is a tiny fraction of a square meter. And so I can't remember what the exponent is, but typically atomic physicists, whatever, they express cross-sections in what are called barns, B-A-R-N-S, which is a little joke. So it's some tiny fraction of a square meter, like 10 to the minus 26, some huge, tiny fraction of a square meter. And it's called that by the idea of you can't even hit the side of a barn. Got it? Right. Or have you heard that expression before?
Mm-hmm.
Yeah, so that's why they're called barns. Ha ha ha. Not as good as beer. But
What can I say?
what can you say? That's right. Oh, I know.
Nah,
No. Viral. Viral.
we can't get the brass out of a barn if we get joke.
What, were we raised in a barn? Yes, Dr. Harmon, it's viral because it's making me sick, they said. All right, optical depth.
I was just very.
Theoretical? Yes. Well, theoretical. This is going downhill. I was just thinking
No time to stop.
Time to stop.
Can't stop, won't stop, Alex.
Optical depth. So this is a very important concept. We're gonna beat the hell out of this basically. It's just gonna be over and over again. So notice I didn't say anything that would get me fined. I'm not going to. It's on camera. So don't you either. So d tau lambda, by definition, is minus kappa lambda rho ds, is the definition for the increment in optical depth in going a distance ds along the beam. Is the increment in the optical depth and going a distance ds along the beam. So notice that it's based on the fact that we've got that e to the minus the d, what I should say, di lambda being minus kappa lambda rho I lambda ds. That's like the stuff that isn't I lambda in there. It's based on that. And we should note here the minus sign indicates that tau lambda increases in the opposite direction to that of light travel as we look back along the ray. In other words, when ds is increasing, tau lambda is decreasing and vice versa. So I'll illustrate that like, ping, there's a light source right there. Here's a beam of light on the way to our eye from that light source. And the point is, S is increasing in that direction, but tau lambda is increasing in that direction. The further away you are from your observation point, the bigger is the optical depth relative to your observation point. So you can talk about what is the optical depth at the location of the source of light. And as we'll see, that's what is going to go into telling us how well can we see that source of light. A source of light that's at a large optical depth for you is hard for you to see. On a foggy day, when you are looking at things at large enough optical depths, you can't see them anymore. They're too far away. Most of the photons from them get scattered before they ever reach Earth. So let's be specific about that.
So does that mean that as we get closer to the sun, we can see deeper and deeper into it? So
No, because the thing is that once you get to the surface, there's almost nothing there anymore. So in other words, outside the sun, the absorption coefficient is essentially 0. So the optical depth is essentially 0 all the way to the surface of the sun, quote unquote, and then it starts increasing.
Okay.
So the answer to your question is, sure, as long as you plunge below the sun's surface, you start to be able to see deeper into, into it. Right? But other than that, so not worth it. But if you didn't have that problem of vaporizing, yeah, the further in you are, the further you can see, sure. All right?
Pour some water on yourself.
That'll take care of it, because the water won't vaporize. You'll be fine. Yes. You've got a lot to learn.
Just drink a lot of cool.
That's right. Yes. Wow.
Overheat.
My students are geniuses. So,
Revolutionize the burger.
all right. So let's imagine we're looking at the star, and there's the top of the atmosphere, which there's no such thing. A star just fades away into space. But we could pick some level where there's not much star left and kind of arbitrarily declare that to be the top of the atmosphere. So top of atmosphere, ignore the fact that that's not really a well-defined concept, just mean yellow. So z-axis will be perpendicular to the surface. Here is light heading off from some point within the star, buried underneath the top of the star's atmosphere, off in some direction theta, away from the vertical toward the surface. And we're going to say that the point that we're considering is S is equal to 0. It'll have some optical depth which is greater than 0 for our observer who is looking along that direction into the star. And at the top of the atmosphere, the optical depth is 0 because essentially there's no absorption. Rho is 0, for that matter, capital M is essentially, well, no, because there's a few atoms. Essentially, rho is 0 down to the top of the atmosphere. So the optical depth at the top of the atmosphere, we call that 0. And then as we go deeper and deeper in, the optical depth increases. And then meanwhile, how did I put it here? Yeah, I'll put the same way. Draw an arrow this way. That's the direction of increasing S along the beam. Right, so again, this idea that S increases opposite to the direction that tau lambda increases. S is increasing as you move outwards, tau lambda is increasing as you go inwards. So the change in tau lambda between any 2 points will be add up all the d tau lambdas. So as we move along the beam here, we can add up all the d tau lambdas between tau lambda and 0. In other words, I'm just going to choose to go in the same direction the beam is traveling when I do this integral. I'll start at our source here at s equals 0 and move along here. I'm in the direction of decreasing tau lambda. So I'm going from tau lambda to 0 d tau lambda. So that would be 0 minus tau lambda. In other words, that's going to be minus tau lambda at the point in the direction I've chosen to do the integral. And then putting in the d tau lambda is minus kappa lambda rho ds, that'll be the integral from 0 to the location of the observer of kappa lambda rho ds prime. Because d tau lambda is minus kappa lambda rho ds. So this says tau lambda is the integral from 0 to s of kappa lambda rho ds prime. So in other words, the optical depth at this location I can get by integrating kappa lambda rho ds with a plus sign from 0 to wherever I want to be. And essentially that would be integrating out to the surface because nothing happens after that. There's no more absorption after that. Now, let's notice something here. Since we made quite a to-do of showing that the mean free path was 1 over kappa lambda times rho, then we have that tau lambda is equal to the integral from 0 to s of ds prime over L lambda, right? Because kappa lambda rho is 1 over L lambda. So, in other words, we keep adding up the little ds divided by the local value of the mean free path. This can vary along the mean. The mean free path doesn't have to be constant. Vary with position along the mean. So what this is saying is that the optical depth is the number of photon mean free paths between the source and the observer. Distance over mean free path will be the number of mean free paths in distance ds. Number of photon mean free path lengths between source and observer. For example, if you're not buying it, for example, what if the mean free path happened to be 1/10 of a meter in some location and ds was 1 meter? Well, if the mean free path was 1/10 of a meter and ds was 1 meter, that contribution would be 10 mean free path lengths in that 1 meter there. So if I add up number of mean free paths in ds prime for all the ds primes, that's the total number of mean free paths. So a good interpretation of the optical depth is it's how many photon mean free path lengths there are between you and the source of the light. If there's lots and lots of mean free paths, then the photons will scatter many times before they would reach you. In other words, they're not likely to get to you. If, on the other hand, there's only a fraction of a photon mean free path between you and the source, most of the photons will make it to you. So the optical depth is a measure of how likely photons are to get to you. The more mean free paths between you and the source, the less likely photons are able to traverse all the way to you without interacting first, is the idea. Okay, any questions?
I can be a little confused on that. You said, I thought you said the mean free path was when it's not being collided with.
The mean free path is the average distance between collisions.
So if the average distance is higher, how is that less likely to reach you?
Because, no, it's the other way around. If the average distance between collisions is larger, it's more likely to get to you.
Okay.
Yeah, so the idea is, in this room, the photon mean free path is quite large. Photons can go quite a ways before getting redirected. That's why we easily see one another. Almost all the photons that we're reflecting towards one another make it to one another's eyes. On the other hand, fill this room with a fog. In that case, many of the photons will run into a fog particle before they get to you. The mean free path is smaller because there's all these fog particles that the photons can interact with. And so when the mean free path becomes small compared to the distance between you and the source, that's when you're going to have trouble seeing it. That's when it's going to be almost no photons make it unscathed to you because you're far away compared to the average distance photons can go before getting scattered or absorbed out of the beam. So why is it hard to see on a foggy day? Because it's hard for a photon to make it to you without getting scattered or scattered or absorbed before it gets to you. Thanks, fog particles. So, if we look at our expression here for tau lambda, we can rewrite the expression we had before. Remember we said I lambda is I lambda naught e to the minus that integral, 0 to s of kappa lambda rho ds prime. But that integral is minus tau lambda, right? Tau lambda is the integral with a plus sign, so the integral with a minus, in other words, that's e to the minus tau lambda up there. Our expression becomes I lambda is I lambda naught e to the minus tau lambda. So in other words, 2, 4, 6, 8 time to not exponentiate, now it's time to logarithmiate. If we take logs and then solve for tau lambda is the natural logarithm of the initial beam intensity divided by the beam intensity wherever you are. So the smaller I lambda has become, the bigger tau lambda has gotten. So this is what tau lambda is. It's the logarithm of how bright it started out over how bright it is now. That's what it comes down to. So if I lambda naught over I lambda is E. If you're at a place where the beam is only 1 over E of what it started as, what's the optical depth? 1. So a source at an optical depth 1, only 1/8 of the photons are getting to you, because the intensity is down by a factor of 1 over E compared to what it started as. Only 1 over E of the photons reach you unscathed. What fraction reaches you for tau lambda equals 2? So if tau lambda equals 2, what does this ratio need to be? Not 2e. E to the 2, e squared. So only 1 over e squared of the photons reach you. Etc. 1 over e to the optical depth is the fraction of photons that reaches you unscathed. What's the in Fermi problem speak? 1 over e is equal to, as in it's a simple fraction that's about 1 over. No, that's not as good as 1/3, right? Because e is like 2.7 something, 2.78, whatever, right? So 1 over e is about 1/3. So at an optical depth of 1, about 1/3 of the photons are reaching you. So if you're in a fog and somebody's at an optical depth of 1/3 of the photons from them are getting to you unscathed. You'll still be able to see them, but they'll look hazy, right? If they're at an optical depth of 2, what fraction of the photons reach you, roughly? About a 1/9 of them. It's a little more than that because it's, it's 1/3 was an underestimate, so maybe an 1/8 or whatever. They're starting to get pretty hard to see. At an optical depth of 3, they're pretty much fading away. So, you know, when somebody walks away through in a fog, there's no such thing as the distance at which they disappear, right? They just fade away. But in other words, at an optical depth of 2 or 3 or so, it's getting really hard to see them, is what it comes down to. That's how we can interpret what the optical depth means. And the thicker the fog, the smaller the physical distance that corresponds to a given optical depth, because we have that proportionality to how much absorption and scattering is going on. More absorption and scattering means optical depth increases faster as distance increases. So a thicker fog produces a given optical depth at a closer distance to you, which translates into, wow, I can't see as far through this fog as I could through that fog the other night. It wasn't so bad, blah, blah, blah. And notice, though, in a fog, it's not that the photons are disappearing, it's that they're getting redirected. So in other words, when there's a fog, you look around you, you see white haze everywhere. Why are you seeing that? What you're seeing are photons which have been scattered towards you after, quote unquote, bouncing around, after entering fog droplets and getting redirected maybe more than once, so that by the time the light reaches your eye, you can have a photon. If there's a thick fog in this room, there's a photon that came off of Alec and it was originally going to come right to my eye, and all the photons coming from some point on Alec's face get focused to a corresponding point in my retina, and you do that everywhere, and I see a nice image of Alec or you or whatever, right? But if there's a fog, instead what's happening is, oh, whoops, it got redirected. That's not going to be seen by me in the direction it was originally coming from. Oh, it got redirected again. Now here it comes to my eye, but that means my retina focuses it corresponding to a point in that direction, not to where it was originally coming from. So in the fog, then things become less distinct because photons are getting redirected. You're not seeing them in the directions they originally came from. Meanwhile, all around you, you see hazy light because you are seeing photons coming to you from directions where they wouldn't have come from if the fog were not there. And that's what's happening inside of a star. If the sun were completely transparent, we would just see a blindingly bright nuclear furnace in the center. We'd be seeing gamma rays if they could make it all the way to the surface. So it would be intensely bright because it would have visible light corresponding to a temperature of 15 million Kelvin. Ow, 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 brilliantly, blindingly bright core of the sun. And if you were inside the sun and were completely transparent, you'd be just, oh, look at that blindingly bright core of the sun. Instead, what happens is, because the sun's gases are opaque, is when you're inside the sun, you can't see the core because the photons, the mean free path is way smaller than the distance to the core, and so you cannot directly see the core. Those photons are not coming in to you from the same direction they were when they were emitted. On the other hand, you look around you and there's brilliant, blinding light everywhere, but that's because those photons, while they got their origin in the core, have been redirected every which way, and so you're surrounded by photons coming at you in directions that are as a result of their having been scattered multiple times, or absorbed and quote-unquote re-emitted, as opposed to coming directly from their source, which is the core of the sun. So that's what's happening in a star, or a foggy day on Earth, minus the nuclear core. So, in a sense, this is the nuclear cores of the sun, and then the fog is the nebulous, whatever. Anyway, that's what we want to study in more detail when we're studying radiative transfer through a stellar atmosphere. That's ultimately what's going on, is that the light is getting scattered, redirected, absorbed, et cetera, on its way out to the surface. So we're going to talk about what happens at any given depth, and then what do we see when we're outside the star. Okay, any questions? Yes?
This might be a little far-fetched, but since the scattering doesn't happen at the same place every single time, like it's still a little random, would the object kind of twinkle, since your eye would perceive it from one point and then scatter at a different location, or perceive it at a different location, where it kind of twinkle back?
It doesn't for that reason particularly, unless, I mean, there's something kind of similar to that. In other words, if the fog particles are big enough and separated enough that you can see them individually, which happens sometimes, where you can actually see little water droplets, then yeah, that's essentially what's happening, because, you know, if I look at somebody, they shimmer because I've got these particles that go in front of them. And if I can see the individual particles, I'm seeing light directed to me by the locations of those individual particles. So in that case, yeah, it's not called twinkling in that case, but it'll have this shimmery appearance because I can actually see the scatterers. On the other hand, if there are enough of the fog particles and so that they're, you know, densely spaced and they're small enough I'm not seeing them, then it'll just average out and you wouldn't notice that twinkling like that.
Okay.
Twinkling that we see of stars at night is due to a different phenomenon. It's because the air is turbulent, and so there are pockets of warmer and cooler air that have different indices of refraction, and as a result, light rays get bent every which way in random directions, and so that rapidly varies, and so we see the shimmering, twinkling of the light. Okay, yeah, good question. Alrighty, so notice back to our figure here that the optical depth corresponding to a given geometrical depth, in other words, how far we're looking into the star, is going to depend on that angle theta, on the angle that you're looking at. And in fact, this is the origin of lunar, which is so important for studying star spots, for example, with my method. Note that the optical depth, and it's also, it explains why stars get dimmer as they get closer to the horizon. The optical depth corresponding to a given geometrical depth depends on the value of theta. So if, as we did in observational, if we approximate the atmosphere as being so-called plane parallel, and as long as you're pretty close to the surface, that's not a bad approximation. In other words, you ignore the fact that the star is really a sphere, and locally, just the top of the atmosphere is, of course, really curved because it's part of the sphere. Ignore that. That's a plane parallel atmosphere. If we assume a plane parallel atmosphere, then tau lambda is 0 to s, integral 0 to s of kappa lambda rho ds prime, where s is measured along the beam direction. Geometrical depth means how far physically below the nearest point on the surface you are. So by geometrical depth, we mean how far under the surface, how far under the top of the atmosphere are you. if you take a straight line up to the nearest point. So if we say that that is h for geometrical depth, then this will be, if we just go along the z-axis, integral from 0 to h of capital lambda rho times dz over the cosine of theta. Because if we look along our path here, that diagonal there is a slice ds. Here is dz. So ds and dz make that angle theta with respect to one another. So dz is ds cos theta. So ds is dz over cosine theta. Yes?
In the second integral, is the p supposed to be a subscript, or the rho supposed to be a subscript, or is it?
Oh, no. No. Thank you. It is definitely not. No. Well, what's one over the cosine theta? There's another name for that. I seek your answer. I seek your answer, but I can't hear it. Secant, yes. Very good, you came up with it. Yes. So, that'll be secant of theta, which for our beam direction here stays constant. Right? So, we can pull that out there. We'll have secant of theta times integral from 0 to h of capital lambda rho dz. And we're going to call this the so-called vertical optical depth. In other words, the optical depth if we were at theta equals 0, if we were going straight down instead of looking in at a slant. And we'll give that the symbol tau lambda v, the v meaning that it's vertical. So this will be tau lambda v times the secant of theta. So tau lambda, the vertical optical depth is tau lambda for a vertically traveling photon. Well, I'll just say for a vertical beam. This will be a little more general than that. For a vertical beam. Apparently I did not turn my sound down on my phone. And so now it's happily informing me that I'm only 10 minutes away from my advising appointment. Isn't that great? So, we'll finish up by reminding you that you saw this before, and I didn't call it this because I didn't want to complicate things. But in observational, remember when we talked about air mass? It's exactly the same idea where you've got a little tiny person, Earth's atmosphere, and at the top of the atmosphere. Instead of looking at some point within a star, there's a star. There's the guy who says, "Okay," and runs over there. So when you are observing the star at angle theta, remember there what we did is we said that z was the zenith angle, the angle from the zenith, the point overhead, and that we said that the air mass was x equals 1 for z equals 0 when you're looking straight up, And that it's secant z if you look away from that, because that's how much further through the atmosphere you have to look. So it's exactly the same thing. The optical depth is, for a plane parallel atmosphere, secant of z slash secant of theta times bigger than for light that's just traveling vertically, taking the shortest possible path through the atmosphere. So you have met this before, but now we're going to apply it to looking inside stars as opposed to looking at stars through our own atmosphere. The end.
Fin.
What's that?
Fin.
Fin, yes. I was back when we were doing like a little college reunion thing, we were playing The Sound of Music.